It's on. I'm done. Wait. Yes. I now call to order the 2411th meeting of the Philosophical Society in the 149th year since its founding on March 13th, 1871. Good evening, everyone. Good evening. My name is Larry Milstein, as some of you seem to know. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., dedicated to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Jared Kaplan in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. Tonight is the Society's annual meeting, and we will begin with a brief summary of the Society's activities and its finances during the fiscal year that ended on June 30th. And we will have a report of the Audit Committee on the finances and books for the fiscal year. Thereafter, we will make a few announcements, followed by a reading of the minutes of the 2410th meeting and the annual Joseph Henry Lecture by Brian Keating on the Big Bang and inflation. We will then turn to this evening's lecture, followed by a question and answer period. When the Q&A session is done, I will present a thank you gift to our speaker, make a few closing announcements, thank those who make PSW possible, and adjourn the meeting to the social hour. First, please join me in thanking the sponsors of the 2019-2020 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a very generous donor who wishes to remain anonymous. And tonight, please also join me in thanking our member, Carl Merrill, Scientist Emeritus at the National Institutes of Health. Carl, thank you very much. Carl is a man of many talents. In addition to his many contributions to molecular biology, he likes to play a double slit experiment in his basement. And when he's frustrated with the outcome and can't reverse it to his content, he likes to drive a Ferrari. And when he's not doing that, he's founded a company to develop the application of bacteriophage to curing bacterial diseases, in which he's had some considerable success. So Carl, thank you very much. So now for the part of the evening where you have to bear with me, the annual report. As required by the bylaws, this is the Society's annual meeting in time for the President's annual report on the Society's activities and finances for the fiscal year, and for the annual report of the Audit Committee. It is also a chance for those who enjoy the lectures live, online, and in recorded videos to get an idea of what goes into producing PSW events and recordings and about the Society and its affairs. Hopefully the information will offset the time it takes to convey it and inspire continued interest and support of PSW science. First, keep in mind, PSW is an entirely volunteer organization. Neither the officers nor others who work to stage these events, do recordings, or take care of office work are paid or receive compensation of any other type for their service to PSW. And we're very happy to report positive growth in both membership on the General Committee and in volunteers helping PSW in the past fiscal year. Please thank them all. Programming was very strong this year by all accounts. Highlights included the planetary definition debate, Alan Stern and Ron Eckers, Brian Keating's talk on inflation, and the back-to-back presentations by Zibby Turtle and Steve Squires on the proposed Dragonfly and Caesar missions. For those of you who haven't been following this, NASA selected Dragonfly, which I think was the audience favorite by quite a bit. And this year's programs look as strong, and we're hoping to add 1 or 2 additional events. So we'll have 2 more than last year, fingers crossed. Membership is growing and at an increasing rate. In fact, new memberships in the past fiscal year were more than twice the year before, and far more than any other year in decades. So far, it looks like this year is off to a very good start as well. Lecture attendance continued to grow and is approaching 100, up from just 84 5 years ago. In addition, live stream viewership has been growing steadily to about 30 per lecture, augmenting the in-person live viewership by over 25%. Dinner attendance also increased over last year, averaging almost 30 for regular dinners, and the Society enjoyed record attendance at the Henry Dinner last May. All good trends. Were live streamed and recorded. The recordings were edited and posted to the PSW Science YouTube and Vimeo channels, which now have 130 videos. Subscribership and viewership are growing on both channels. PSW has over 3,200 YouTube subscribers, and several PSW videos have been viewed more than 100,000 times. Overall, PSW videos have been viewed over 325,000 times. Work on the website is ongoing with various improvements on the front end and the back end and content additions. Almost all the Henry lectures have been posted, and PDFs of the original 15 volumes of the PSW Bulletin that have been reprinted have also been posted. In addition, the last volume, number 16, is being reprinted now and will be posted as soon as possible. PSW social media presence also continued to grow. The PSW Science Meetup Group has over 1,600 members and is among the largest meetup groups in the DC area. And the Society is making more and better use of Twitter to announce events and selective items of interest to PSW members relating to PSW and to PSW speakers. The Society has migrated virtual virtually all its communications and record keeping to digital media and digital platforms. The Society's finances saw a further improvement this year with substantial growth in dues payments, individual lecture sponsorships, and major donor gifts. The number of dues-paying members is almost double what it was 10 years ago and has grown about 50% in the last 5 years. Individual lecture sponsorships last year reached half of the Society's goal of having at least one individual sponsor for each lecture. This is roughly double the number 5 years ago. Contributions exceeded expenses last year, and the Society was able to add to its reserve funds, and the Society's investments grew in value and produced dividends and other income. In sum, the year was good. Strong programming, growth in membership and attendance, further growth in media and social media offerings, income well above expenses, and further growth in financial reserves. But this is not to say that the Society does not face challenges. Like any vital organization, it's an ongoing project. And as a result of successful years like fiscal 2018, 2019, it will have to address growing needs for volunteer services and active, dedicated leadership, increasing expenses, and the inevitability of change and the necessity of adaptation. The Society has made considerable progress towards its 10-year and long-term goals, but it has more to do. Given the enthusiasm and skills of the membership, I have confidence that the Society will take the challenges as opportunities and make the most of them. Detailed financial reports are available from Corresponding Secretary Taylor. Sincerely, Larry Milstein. James Heelan now read the report of the Audit Committee for the past fiscal year.
This year, I served as the chair of the Audit Committee. I'm pleased to report we have audited the records and financial reports of the Operating Fund and Restricted Fund of PSW Science, founded 1871 as the Philosophical Society of Washington, including the attached balance sheet, which I have here, as of June 30th, 2019, and statements of receipts and expenses for the period of July 1, 2018 through June 30th, 2019.
Is your mic on?
My light is on.
Okay.
While our audit would not necessarily disclose all errors, we found no evidence of material errors or omissions. In our opinion, on behalf of the committee, the financial statements are fairly stated. We wish to commend Brett Magaram, Treasurer, for his service to the Society. Signing for the Audit Committee, James Heelan.
I'm going to add a special plug for the person who actually enters all the data and responds to all the questions that people have about their dues and many other things, which is our Corresponding Secretary, Robin Taylor. And now we can turn to tonight's meeting. I am pleased to announce that the following new members have been elected to the Society. Adam Jacobson, a senior research engineer at 26 Labs, interested in programming languages, computer security, and nuclear energy, who was introduced to PSW by his friend Will Angel. Thomas Erickson, senior specialist advisor on business process and strategy with NTT Data. interested in innovation and management, energy storage, material sciences, and new and renewable energy sources, who originally learned of PSW from the Washington Post. Mike Helton, an aerospace engineer now with Helton Associates, interested in space exploration, especially space mission design and operations, and in risk management. Mike learned of PSW from a friend. Elisa Vermilli, an IP attorney with AstraZeneca Pharmaceuticals. It's okay, I'm an IP attorney too, so. With broad interests in science and technology, who comes to membership through friends and attending PSW events. Thomas Weir, National Institutes of Health scientist emeritus, a pioneer in the study of seasonal effects on mood, particularly interested in the physics of gravity, who comes to PSW through PSW member Carl Merrill. Elizabeth Weir, a senior public health analyst with the National Institutes of Health, National Institute of Child Health and Human Development, with a wide range of scientific interests, especially women's health and health policy, who comes to PSW through PSW member Carl Merrill. I suspect Alice Merrill may have had something to do with it too. Andrew Abraham, an attorney with the U.S. Department of Justice and a returning PSW member interested in technology, especially physics. Nicholas Gorgon, a doctoral student in astrophysics at George Washington University, interested in physics, particularly astronomy, statistics, data science, and software engineering, who learned of PSW from a friend. Jonathan Ogiano, a cyber and artificial intelligence consultant with ECS Federal, interested in brain-machine interfacing, artificial intelligence, understanding consciousness, and disruptive technological change, who learned about PSW from a friend. And tonight's speaker, Jared Kaplan, whose background and interests, in part, will be clear to you from tonight's proceedings. Please join me in welcoming them all to membership. PSW gifts a signed reprint of Volume 1 of the PSW Bulletin to all new members. If you are a new member and you have not yet received your signed copy, please see me after the lecture and I will give you one. And if you purchased a PSW ribbon and you haven't picked it up yet, please see Social Media Director Ann McQueen, and she will provide you with your ribbon. Recording Secretary James Heelan will now read the minutes of the 2410th meeting and the 88th Joseph Henry Lecture by Brian Keating on the Big Bang and Inflation, delivered to the Society and guests on May 17, 2019. James.
Thank you, Larry.
Is it on? It's not here. Yeah, okay.
I think it's on. It's good to see you again. On May 17, 2019, in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 88th Joseph Henry Lecture and 2410th meeting of the Society to order at 8:02 p.m. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Brian Keating, Professor of Physics, Center for Astrophysics and Space Sciences of the University of California at San Diego. His lecture was titled, The Big Bang and Inflation, Glimpsing the Beginning of Time from the Ends of the Earth. Keating began by discussing what he called 5 great debates in astronomy. The first was Galileo Galilei's revolutionary early 17th century use of the telescope to observe the sky and to contradict geocentrism. The second great debate took place approximately 100 years later in England, when William Herschel developed Leviathan, a telescope approximately 1 meter across and 10 meters long. With Leviathan, Herschel mapped the Milky Way galaxy and erroneously placed Earth's sun at the galaxy's center. The third great debate was what is commonly known as the Great Debate, which began on April 26, 1920, at the Smithsonian Museum of Natural History. That debate addressed whether observed nebulae were part of or far away from the Milky Way. In 1923, Edwin Hubble determined that the nebulae were outside of our galaxy. The fourth great debate, from 1930 through 1965, asked whether the steady-state model or the Big Bang model accurately described the universe. The Big Bang model won. The fifth great debate is ongoing, addressing whether our universe is just one of an infinite possible numbers of universes, called the multiverse. Looking out into the universe, scientists have observed other galaxies, the Dark Ages, and the recombination era in which the cosmic microwave background formed. Scientists are now working to see into the first trillionths of a second after the Big Bang for evidence of inflation that would prove the existence of the multiverse. Some scientists predict that if inflation took place, there would unavoidably be waves of gravity permeating the entire cosmos. And if true, light from the time of the CMB would shake up the polarization of the CMB in a predictive way called B-mode polarization. Using the BICEP-2 microwave telescope, Keating's team searched for polarized light arising from the interaction of light with electrons in a B-mode class, which Keating said can only come from gravitational waves. BICEP-2 was mounted in Antarctica for its low water vapor and its relative cost-effectiveness compared to a space-based telescope. After 1 year of observation on March 17, 2014, without peer review, Keating's team announced the detection of B-mode polarization, indicative of the presence of primordial waves of gravity, in turn, indicative of inflation, and therefore the multiverse. The team was immediately lauded by prominent physicists and the media and predicted to be awarded the Nobel Prize. But interstellar dust is ubiquitous. And Keating's team ultimately concluded that they were deceived by such dust and had not seen evidence of the early universe. Keating said he has learned from his mistake and now leads the Simons Observatory, a new CMB experiment being built in the Atacama Desert of northern Chile, due to begin observations in 2022. The observatory will search for B-modes using a 6-meter telescope joined by 3 small aperture telescopes, simultaneously scanning at 6 microwave frequencies. Light will enter through a receiver and be cooled to 0.1 degrees above absolute zero. Its detectors can see simultaneously 2 different frequencies and polarizations. These technological advancements will hopefully eliminate the deceptive effects of interstellar dust. Keating thus remains optimistic that learning from mistakes in science will lead to further discovery. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:07 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 25.5 C. Weather, cloudy. Attendance in the Powell Auditorium, 151, and viewing through the live stream on the PSW Science YouTube channel, 33. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any corrections to the minutes or comments thereon?
Well done.
Well done. Hearing, yes, Carl.
I don't know if you want to add it, but
Speak up.
I don't know if you want to add it, but it might be nice to mention that a free copy of Keating's book was made available.
Carl comments that we might add to the minutes that Brian Keating offered us free copies of his book called Losing the Nobel Prize at the meeting. I'll leave it to James to decide whether he should include that or not. Thank you for that, Carl. Are there any other comments? amusing or otherwise? If not, I will entertain a motion to accept the minutes as read. And a second? Second. And all in favor? Aye. All members opposed? The minutes are therefore accepted as read and will be posted to the website in due course. We now turn to tonight's lecture on quantum gravity, why it's different. It's my pleasure to introduce tonight's speaker, Jared Kaplan. Jared is Associate Professor of Physics at Johns Hopkins University. He's been a visiting professor at the Stanford Institute for Theoretical Physics and the Physics Department at UC Davis, and he was a research associate at SLAC. He's broadly interested in effective field theory, particle physics, cosmology, scattering amplitudes, and the conformal field theory bootstrap. His research currently focuses on using the conformal field theory to learn about quantum gravity and on collaborations and computer scientists in learning research projects. Honors and awards from the Simons collaboration on the recipient of a grant from the Simons collaboration on the non-perturbative bootstrap, an NSF grant, Hopkins Award. He was an Alfred and a Kavli Fellow, as well as the recipient of a fellowship, a National Science Foundation Research Fellowship, and the James Mills Pierce Fellowship of Harvard University. He has offered numerous peer-reviewed publications, organized several technical conferences, and has given many invited lectures. He earned a BS in Physics and Mathematics at Stanford, and a PhD in Physics at Harvard, where his PhD advisor was PSW member and peripatetic theoretical physicist Nima Arkani Hamed. Please hold questions at the end of the lecture, and join me in welcoming Jared to the podium. Okay.
Thank you very much for that wonderful introduction. It's really an honor to be here today. I've heard a lot about this society from my scientist friends, so it's really exciting to be able to address you as an audience. Some of those words you heard about the work that I do were a mouthful. So I should just tell you to start with that this talk is really about why quantum gravity, the combination of quantum mechanics with the gravitational force that's holding us all down in this room, is a really exciting thing to think about. Theoretical physicists, scientists, we're all envious of the great discoveries of the past, the discovery of things like special relativity and quantum mechanics that really, at a kind of foundational level, change the way we think about what the world is that we live in, what the universe is. And so I'm going to explain why some of us think that quantum gravity, if thought about in the right way, in the deepest way, may usher in a similar, or has ushered in a similar revolution in how we think about space-time. So the title of the talk is Why Quantum Gravity is Different, and so you should naturally ask, different from what? What I mean here is different from our description of all of the other particles and forces in the universe, which currently is codified in a comprehensive theory called the Standard Model of Particle Physics. Now, the Standard Model appears to describe basically everything that we've tested, and depending on how you think about it, it might seem rather complicated. If you've heard anything about it, it involves quarks and leptons, various different kinds of bosons that are pictured here, most recently discovered the Higgs boson. A lot of these have various weird names like strange and bottom. So it might seem like kind of a mess. But actually what I want to emphasize is that from a high level, from a conceptual level, all that's really going on in the Standard Model, there are a bunch of particles, and there are 3 kinds of forces. Those 3 forces are all very, very, very similar, and the different particles differ based on which forces they talk to. So the force that I'm guessing many of you are most familiar with, and may have studied in school at some point, is the electromagnetic force. And it has various manifestations. So here we have opposite charges attracting, and there are various field lines from the electromagnetic field that you can think about. Like charges repel, unlike charges attract. And we have an exciting manifestation of electrostatics, charge jumping across space, making a pretty picture. Another very useful manifestation of the electromagnetic force is that it has this magnetic component. We can run currents in wires and generate magnetic forces, which are mechanical forces, and make electric motors. And then a very neat unifying theme is that not only is there this electrostatic picture and this magnetic picture, but this theory also explains light. If you jiggle these charges here, then you cause little jiggles, little ripples in the electromagnetic field lines, and those go sailing off to infinity, and then you get light, radio wave, gamma radiation, etc., as vibrations of this underlying electromagnetic field. So that's the electromagnetic force in short. What I'm going to tell you very briefly is that electromagnetism, the weak and the strong forces are all very, very, very similar. So I've tried to picture this here. The weak and strong forces may seem very different, and there are ways in which they're different from electromagnetism, but actually they're really just kind of like a souped up version of the same old electromagnetism. The W and Z bosons, which are associated with the weak force, are basically just like heavy versions of the photon. And the strong force is roughly like 8 photons all working together. They're all basically twins of each other. They're so closely connected. We don't give each of the 8 its own name. If they were really octuplets, I guess that would be child abuse. And so that's really it at a very high theoretical level. And so there's a lot of similarity and repetition in the Standard Model. Now, a question you might wonder about very naturally, given that all these forces are very similar, is the same thing true of the gravitational force, the other force that's most familiar to us? And of course, there are a lot of reasons to think maybe so. Here we have the Earth orbiting the sun. It's being held there by the gravitational force. That was a very useful and prescient metaphor for the structure of the atom, for electrons orbiting nuclei in atoms. And so you might be led, for example, by this picture. In fact, there are mathematical details I'm not going to go into that are identical here, to think that gravity is really also a lot like the other forces, and that there's some way of kind of putting gravity together with a Standard Model that's just the same business as usual approach, and we can understand gravity. And so the point that I want to make by the end of this talk is that in the last few decades, it's actually become increasingly clear that on a fundamental level, gravity is so different from the other forces that thinking about it carefully has triggered a revolution in our understanding of space and time. So here's an outline. That was a bit of a preamble. Here's an outline for my talk. In the first part, I'm going to tell you about the Standard Model and the discovery of the various forces and particles in the Standard Model, and how all those philosophically followed from a pursuit of a reductionist program, taking stuff apart and looking at what it's made of, and using that to understand what's going on. This is the Philosophical Society, so I can be a bit of a philosopher. Along the way, I'll explain something that maybe you know, maybe you don't, which is, why are we high-energy physicists? My field of physics that works on things like the Standard Model and quantum gravity is often referred to high-energy physics. But why? Why is that a unifying theme? I'll explain. It follows quite simply from a few things that you've probably heard of. And then in the second part of the talk, I'll address a question that you might wonder about when reading about discoveries in physics and new projects in physics, which is, how do we know that there actually are new things to discover? Specifically, how do we know, for example, in this reductionist program, that if we take things apart, we're going to actually find new constituents, new ingredients, something interesting to keep us up at night? And I'll explain how basically very weak interactions and tiny effects can point toward some new thing happening at very, very short distances that we can get excited about and we can use to motivate further experiments. And then in the third part of the talk, I'll discuss why, at a fundamental level, it seems like none of this reasoning actually works when you think about gravity. A little bit of it works, pointing towards very short distance scales, but a lot of it really fails in a dramatic way. And fortunately, as actually often happens in theoretical physics, the way that one approach fails provides some insight into what other way of thinking might get you there. And I'll talk about that and kind of conclude by explaining that we need a new so-called holographic approach to understand quantum gravity. So to start out with, I'm going to talk about how did we get to our present understanding of the laws of physics. So pictured at left, we have the Atlas detector of the Large Hadron Collider. I think there's a person here to see scale. This is a really, really big sci-fi scale experiment. And you might wonder, why do we need these big accelerators, and what are we doing with them? And it turns out the reason why we want them is really because fundamentally we'd like to build a really, really powerful microscope. So all we really want to do is see what matter and energy, space, whatever, what it's all made of. And if we take a reductionist perspective, that means that we want to look at shorter and shorter distances and literally look at what the constituents are that are making up the objects that we see. So of course, this has been followed very successfully. We discovered atoms. Then we discovered that atoms have nuclei. Those nuclei are themselves made of lots of particles, protons and neutrons. We took apart those protons and neutrons and found that they're made of quarks. But really, the goal here is just to have a microscope, to be able to look at matter at shorter and shorter distance scales to see what it's made of. And then, hopefully, we can understand better what's going on at larger scales based on the fundamental rules for these smallest of objects. So that's what you do with a microscope. So you might wonder, why not literally use a microscope? And the reason why we don't literally use microscopes is that trying to see at very short distances requires a lot of energy. So here we have a picture of a water wave. This is an illustration of a light wave, electromagnetic radiation, the radiation we use to see with light with a microscope. And the issue is that if you want to use waves to see something, you need the wavelength to be the same size or smaller than the object you want to resolve. If you have ocean waves and they crash into the side of an aircraft carrier, if you have some long sort of waveform crashing into an aircraft carrier, then you know that because the wavelength of ocean waves is typically small compared to the size of an aircraft carrier, waves are going to get deflected, and if you look at what the ocean looks like beyond the aircraft carrier, you'll see signals that that object was there. Whereas if you just have, say, a pole sticking up in the ocean and you have a big wave, it'll basically just pass through that pole and you'll barely be able to detect there was any effect. So that's the intuition, and it's true for light as well as for ocean waves. And all electromagnetic radiation is just different wavelengths. So all of these different names, from radio to gamma ray, are just different names for electromagnetic radiation with different wavelengths. And if you want to see objects that are smaller and smaller and smaller, you need shorter and shorter wavelength or higher and higher frequency light or photons. And something you may know is that as you go to the right in this plot, in this little diagram, you're getting higher and higher energy light. Now, that's not just a statement about light. That's actually a universal fact. So you might think, oh, well, this is because you're using waves to look at something. Maybe we can use something else and this rule would apply. But actually, fundamentally, because of quantum mechanics, our desire to build a microscope to see things at very short distances turns into a need for very high energies. Roughly speaking, the Heisenberg uncertainty principle says that if we want to look at really, really small distances, then we need really big energies because the product of these two things has to be big compared to Planck's constant. The Heisenberg uncertainty relation is an inequality, and that means that small distance means big energy. And so you can't resolve very short distances, you can't build a really powerful microscope without huge energies. Now you might also wonder, well, okay, so if this is a universal thing, why don't we use light in accelerators? Why don't we take, say, a proton or a quark, an electron, and just shine light at it and see what it's made of? And the reason is that it's actually hard to give light a lot of energy. Light is neutral, so you can't push on it. I mean, I've never tried, but if you try to grab a photon and push on it, you won't do very well. Whereas if you have a charged particle, like an electron or a proton, you can put it in a gradual electromagnetic field and accelerate it and make it go faster and faster. So it's easier to give electrons and protons energy as compared to photons, and that's why we smash them together instead of, say, shining light on some other particle. So that suggests that if you really want to build a microscope, then beyond a certain point, you want to actually build a collider. You want to collide charged particles together at high energies and try to see what they're made of, probing shorter and shorter distances. So I'm going to give you an extraordinarily abbreviated history of collider physics, telling you how we got to our present state of understanding with the Standard Model. We've been at it for a very, very long time. Maybe the first famous collider experiment is that of Rutherford, Geiger, and Marsden from over 100 years ago. At that time, very little was known compared to what we understand about fundamental particles now. In particular, atoms weren't well understood. Many people thought that atoms were kind of like gelatinous blobs, but people really didn't know. And so they did this experiment where they took a thin gold foil and they shot some alpha particles at it and looked at what happened. And the idea was that if really matter was just some sort of gelatinous blob, then the alpha particles would maybe stick a little, lose a little energy, but they'd basically go straight through. But what, of course, famously happened is that these particles deflected at all sorts of large angles. And that suggested, rather than some sort of gelatinous stuff, that actually there were these very, very hard point-like objects, nuclei, atomic nuclei, and that our alpha particles were colliding off of them some of the time and really, really scattering hard like tiny, heavy objects such as billiard balls. And so this was a surprise. This was the discovery of the nucleus. People weren't necessarily expecting it, but it was nevertheless a monumental discovery. And I mentioned that it's a surprise just to compare because some discoveries, we'll see in a second, were not necessarily a surprise. So jumping ahead 50 years for our very brief survey, this is a picture of the Stanford Linear Accelerator 50 years later. And it was an experiment that, this is the detector of an experiment referred to as deep inelastic scattering, which led to the discovery of quarks. So the words deep inelastic scattering, roughly conceptually, you can think of as deep and inelastic, meaning that we're smashing things together really hard and breaking them apart into lots of pieces. So here we have the electron pictured as a baseball smashing apart the proton. And you can tell a very similar story about the proton, actually, that we said about the discovery of the atomic nucleus. If the proton was some sort of blob, maybe the electron would barely scatter off of it. But it turned out that what happened was the electron scattered off of the proton, destroyed the proton, and in some cases scattered very, very hard at large angles off of a few tiny constituents inside the proton, which, upon thought, turned out to be the quarks that make up the proton. So here's another picture of the Stanford Linear Accelerator. I guess I didn't show you a picture of Rutherford's original experiment, but it was a lot smaller than this. It was at a lot lower energy. So doing fundamental physics and building bigger and bigger microscopes is an expensive endeavor. And today, the frontier is the Large Hadron Collider, which is even bigger. And you may have heard that the Large Hadron Collider discovered the Higgs boson. And here we have sort of a plot of when physics experiments happened and how much energy was used. See that there's sort of this exponential growth in energy in order to probe smaller and smaller distant scales. So this is where we're at today. So other collider experiments that I'm not going into discovered the W and Z boson, heavy quarks and mesons, like the bottom quark is heavy, the top quark is the heaviest, etc. And gave us this picture of the Standard Model that seems to explain all of the constituents of matter we currently understand via this reductionist program. Now, a question you might be asking yourself at this point, though, is it's been 100 years. You guys have been building bigger and bigger accelerators all that time, spending more and more money. And you just sort of keep taking things apart and finding more and more stuff. But do we really understand the world better at a conceptual level now? Or is it just that we know more ingredients? And I think we really do understand the world better. So I'm going to give you an example of how this kind of reductionist approach actually illuminates other things that we see on a more macroscopic scale and allows them to be understood. So this is a picture that's probably very familiar from high school, the periodic table of the elements. And it itself is an absolute triumph of science that we understand all of these different elements, all of these different kinds of atoms. But it itself is also quite complicated. It's kind of a zoo here. We have all of these different rows and columns, all these different atoms. And the most basic thing you can observe about this periodic table is that there's about 100 elements, give or take. I mean, here, I don't know, there's 102, there's really more, 118, but roughly, to a theoretical physicist, there are order 100 elements. And you could ask, why is that the case? Why do we live in a universe with 100 elements? What is it about our universe that determined that? Why isn't there only one element, just hydrogen and nothing else? Or conversely, why aren't there millions of different kinds of fundamental elements that are all stable and that you can dig up? And I think this is something we can pretty simply understand. In order for an element to exist, it has to be stable, which means in particular its nucleus has to be stable. Its nucleus is a bunch of protons and neutrons stuck together. The neutrons maybe aren't so much of a problem, but protons have positive charge. They all have positive charge. They're very far away from the electrons that are orbiting around the nucleus of the atom. And we said in the first slide on electromagnetism that like charges repel, so all of these protons are repelling each other, and yet they're all crammed into one tiny atomic nucleus. So what you might expect is that all nuclei with more than one proton are unstable because these protons are trying to push each other apart. Well, it's not as simple as that, because there are also much stronger forces than electromagnetism, but that are short-ranged forces that hold the neutrons and protons and nuclei together. So oversimplifying very, very much, in the case of the strong force, nuclei are held together by some force that's short-ranged, and it's strong, which means that its strength is sort of order 1. The binding energies you get are about as big as the masses of the objects that you're holding together. You have a big binding energy, a lot of force. But conversely, the force of the electromagnetic force is actually comparatively weak. And there's a dimensionless way of saying how strong it is, which is by this number called the fine structure constant, which is approximately 1 over 137. So there's an electromagnetic force that's long-ranged that's trying to make these nuclei fly apart, and there's a short-range but much stronger force holding them together. And so you can ask, when are these nuclei stable? Well, they're going to be stable if attraction can beat repulsion. And attraction beats repulsion if the short-ranged force that's strong is stronger than the long-ranged force of electromagnetism, but this long-range force gets contributions from all of the protons. In other words, if I add a proton to the edge of a nucleus, all of the protons that were already there are going to try to kick it out. And so the number of protons that I can have in my nucleus is roughly going to be bounded by when these forces become equal, because once they're equal, adding more protons is unfavorable. If I try to add another proton, it'll get shot away. And so this suggests that because this force is sort of order 1 in strength, this force is weak comparatively, that you should expect about 100 elements. Well, this is a very, very rough back-of-the-envelope argument, but understanding the basic structure of the strong and electromagnetic forces allows you to deduce very, very basic properties like of the periodic table. So that's an argument for why this reductionist approach really is teaching us interesting answers to sort of why questions about the universe. But there's this other question of how did we know that there was more to discover when we did these various experiments? And how do we know going forward? And there are various different kinds of clues. So the discovery of the nucleus I mentioned was a surprise. It wasn't anticipated. But a lot of the other discoveries that I talked about and many others that I didn't, like the discovery of quarks, the weak force, the W and Z bosons, the Higgs boson, were foreseen and predicted ahead of time. And so how did we do that? How did we know that there was something more to discover, there was something interesting out there? So the kind of question we can ask is, do very, very, very small things actually influence big things that we can see? So we're big compared to the scale of the atom or the quarks. The experiments we do are big compared to the experiments that we'll be able to do that probe even shorter distances in the future. So how, given that we only have access to big stuff, can we detect the presence of new physics happening at very, very, very tiny distances? And intuitively, it seems like it's really hard. If I have some image like this where the pixels are big, I can detect that there are pixels. But if I have a very, very refined image where the pixels are really, really tiny, I can't tell that there are pixels there at all. So this is intuition that it's really hard to tell that there even are pixels if they're small enough. Similarly, maybe it's really hard to tell that the, say, quarks that we have now are made of constituents if they're much, much, much smaller. So it's hard. But there are situations where it's more possible. So there are two kind of broad scenarios, and I'm going to give you concrete examples of both. One is when you break some sort of symmetry. So here is a black image, and if you only look at it very briefly, you might just think it's a solid black rectangle. But there's this little blur here that's some sort of little star. And I think that star is much, much more noticeable because you have a pure black background. You have a symmetry. You have a rule. When you see this, if you didn't see this little blob, you'd say, oh, the rule is this is just pure black. And so something can stand out from the background. And in physics, we talk about this as breaking of symmetry. Another situation is when the effects are very, very tiny, but they add up to something very big. And this is going to be a picture of that. So I'm going to give you an example of both. So this is actually an example of the symmetry. So neutrons in nuclei are fortunately stable. That's a very interesting fact. But free neutrons are not stable, and they only live for about 15 minutes. So on a human timescale, 15 minutes sounds very short. But really, in terms of the fundamental natural scales of particle physics, 15 minutes are more like an eternity. There's a sense, quantum mechanically, in which there's a natural time for neutrons, a sort of time scale on which neutrons quantum fluctuate. And you can think about that if you feel very slightly poetic as some sort of heartbeat of the neutron. And this time scale is incredibly, incredibly small. It's 10 to the minus 24 seconds. So from that point of view, neutrons live for more than a billion, billion, billion of these fundamental heartbeats. And we can compare that to ourselves. It's a billion, billion times longer than how long we live in units of the length of our heartbeat. So from this point of view, physics kind of inverts the question. When you first hear that neutrons live for 15 minutes, you might think, why are they so short-lived? But really the question is, why are they so long-lived? And if they're so long-lived, why do they decay at all? Why don't they just live forever? So the reason why neutrons live so long is that actually they would live forever. They would like to live forever, except for the weak interactions of the Standard Model. So if you turned off the weak interactions of the Standard Model, if you didn't have them, then neutrons really would live forever. But in fact, they can decay via the weak interaction, so that's what this W is. So a neutron can turn into a proton, an electron, and a neutrino. And this was observed and explained to some extent by Enrico Fermi in the early 20th century through his theory of beta decay. But the fact that neutrons live a really long time but not quite forever is a small effect. If you look at a neutron just briefly, you might not see it decay at all. You have to wait quite a long time from the point of view of fundamental physics to see it decay. So the fact that neutron decay is a small effect fundamentally points to something happening at very, very short distances. And so in particular, in the early 20th century, Fermi's theory of beta decay actually anticipated that we would eventually discover the W and Z boson. So very, very specifically, Fermi posited some number called G Fermi, which was basically telling you how fast neutrons decay. And you can rewrite it in terms of units that you're familiar with, like meters, in which case it's about 10 to the minus 16 meters, which is a really, really short distance, much smaller than the size of an atom. And so from Fermi's theory in 1933, you could anticipate that if you only had an experiment that could probe really short distances of this size, which correspond, if you're familiar with particle physics units, to really high energies. This is about a third of the energy of the Fermilab Tevatron, which is this 90s accelerator. So in 1933, you could anticipate that in 1990, you could build an accelerator that would discover something interesting by noting this very weak effect. And this little diagram is showing you that there are all sorts of different length and energy scales associated with various fundamental particles and various experiments. Here we have the Large Hadron Collider, and there's all sorts of question marks about what we might find in the future. So that's one way to anticipate that there's something interesting to discover. It's that there's some very weak effect that you can nevertheless see. Another way that you can discover the same thing is by having some force that is very weak but adds up. So something you can ponder is the entire Earth is pulling you down, but for example, the electromagnetic force between the soles of your shoes and the ground is keeping you from falling into the Earth. If that force wasn't there, you just fall through the Earth. If there was no repulsion between the electrons in my shoes and the electrons in this carpet, then I would just fall through the Earth and fall to the center, and that wouldn't be very healthy for me. But that means that electromagnetism is way, 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 way stronger than the force of gravity. All of the matter in the Earth is working together to pull me down, and a few electrons in my shoes are enough to keep me up. And if you do the math, what this means is that actually gravity is about 10 to the minus 40 times weaker than the electromagnetic force. So that's a lot of billions. It's like a billion, 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 billion times weaker. So the only reason why we know that gravity exists at all is because it combines. Electromagnetic forces don't combine because there are positive and negative charges and they can cancel each other out. So that's interesting. So that means gravity is a very, very weak effect, even though we know about it. But actually, gravity has this interesting behavior, which is that gravitational forces grow with energy. So how do you know that gravitational forces grow with energy? Well, everyone knows E equals mc squared, which means that energy is equal to mass. And something you may know is that gravitational forces are proportional to mass. So that means gravitational forces are also proportional to energy, thanks to Einstein. And that means that if you crank up the energy, if you look at higher and higher energy processes, gravitational forces get stronger. That's not true for the electromagnetic force. The electromagnetic force is just proportional to charge. It doesn't depend on energy really much at all. So what that means is that if you go to very high energies, if you study a very, very high energy experiment, then gravity is going to get stronger and stronger and stronger until eventually this won't be true anymore, and gravity will be just as important as electromagnetism. And via our connection from earlier, that means if you look at really, really, really small things, gravity will become important. And you can, in fact, ask, how short of a distance do I have to get to in order to make gravity be just as important as the electromagnetic force and the other forces? And this distance scale has a name. It's called the Planck scale. It's an extraordinarily short distance. It's 10 to the minus 35 meters. Remember, I told you a few slides ago how it was a big deal that in 1933 Fermi was able to point towards 10 to the minus 17 meters. Well, this is like a million, billion times smaller than that scale that we were talking about then. So it's a really, really tiny, tiny distance. So that means that we know, though, that there's something going on there. There's something, it seems, that's interesting about this very short distance scale. Just like Fermi's theory suggested there'd be something interesting to discover in 1980 or 1990, this suggests there's something really interesting to discover a billion years from now when we build colliders that are probing the scale. So now the question is, should we do that? It would be really expensive. But besides that, theoretically, in principle, can we build a microscope, like one of these really high energy colliders, to smash things together and look at them on this distance scale? The goal there would be to take gravity apart. We took the proton apart and we found quarks. Before that, we took the nucleus apart and found protons and neutrons. So should we take gravity apart in the same way by following this same reductionist idea? So now I'm going to tell you, I'm going to consider this question. So what do I mean by quantum gravity, first of all, and can we take it apart? So what do I mean by quantum gravity? Well, pillars of early 20th century physics include general relativity. General relativity is a theory of gravity and nothing else. So the words relativity might make you think that it's some funny thing involving trains and elevators. It does involve elevators, but really general relativity is just the theory of gravity that we believe to be true. It describes our classical universe, it describes cosmology, it describes the Earth going around the sun, and its most famous feature is that gravitational forces in general relativity can be thought of as curvature of space and time. So quantum mechanics is this other pillar of early 20th century physics, and the Standard Model got its start by combining quantum mechanics with electromagnetism to form quantum electrodynamics. This is what Feynman got the Nobel Prize for. It was what made Feynman's name, is studying quantum electromagnetism. And so the natural thing is, well, we have this force called gravity and we have quantum mechanics. Let's put them together and study quantum gravity. That's what quantum gravity is or would be. However, there is a feature of gravity that you've probably all heard of called black holes, and they're interesting for these considerations of whether we can take quantum gravity apart. So it might seem to you, as if you're not a theoretical physicist, that black holes are these weird exotic objects. There's a black hole at the center of the galaxy. There are some black holes inspiraling and combining together, that's what this is a picture of, that we've recently seen via gravity waves, but those are both exotic astrophysical phenomena. But there's a sense that I want to try to convince you of that black holes are actually sort of the most basic objects in gravity. Why do I say that? Well, no matter what you start with, be it the Earth or a billion Honda Civics or the sun or whatever it is that you'd like to possess, if you cram it together, you'll get a black hole. There's a sense in which black holes are sort of the universal thing that you can always get. I can't build a Honda Civic out of wood. That would be very, very difficult. But if I take this podium and I cram it down to a small enough size, I'll get a really, really tiny black hole. And so there's a sense in which these black holes are actually the universal objects of general relativity. You can always make them. And their most famous feature is related. It's the fact that they're classically inescapable. You can't get out of a black hole. It has a horizon, which is a point of no return, and nothing gets out. So black holes are sort of the most interesting objects in general relativity, and they're also very universal. And the point I want to make now is that black holes mean that you can't take gravity apart, and it doesn't make sense to try. So we went through this logic that there's this Planck scale that seems experimentally totally inaccessible, which is a bummer, but that maybe we want to do experiments at that scale in order to understand quantum gravity. And black holes mean that you can't do that. The whole motivation for being high-energy physicists was to look at short distances. But the problem is that since gravity binds energy together, if you want to look at really short distances like the Planck scale, you need a huge amount of energy, and you need to put that energy all in one place. But what that means is you'll just make a black hole. So if you try to take gravity apart at the Planck scale, what you'll get is a black hole. And you can't then do better. If you try to add more energy to your process to see shorter distances, you'll actually just make a bigger black hole, because the more energy you throw into a black hole, the bigger it gets. And literally bigger, like its size is bigger. Its Schwarzschild radius gets bigger if you add more energy to it. So that means that reductionism, really as a sort of philosophical approach to quantum gravity, doesn't work. It doesn't make sense. It breaks down. All that happens is black holes destroy your microscope, and you might learn about black holes, which is pretty interesting, but you don't take gravity apart and learn about something smaller than the Planck scale. So we can't take general relativity apart. Distances shorter than this Planck length can't actually ever be resolved. When we talk about light observing something, we talk about the resolving power of light. We can't ever resolve the Planck length or shorter. And so all of this logic that built the Standard Model doesn't seem like it can be applied to understand quantum gravity. Fortunately, the existence and the properties of black holes, even their basic macroscopic properties, point the way towards a very different approach to thinking about quantum gravity that actually may be fruitful and may tell us very surprising, very deep things about our universe. But first, in order to highlight why black holes are important, I'm going to give a brief detour that might seem unrelated. So something we all like to do on our phones and our computers, et cetera, is to store lots of information. I guess this device is almost antiquated, but this is a hard drive. And the way that hard drives store information is by having tiny little bits of magnetic material, and the magnet can point up, and that means, say, 0, and the magnet can point down, and that means 1. And we can therefore abstractly visualize this storage of information as having some region. This is a volume. It's the interior of a cube. And we can have a bunch of magnetic material in this cube. And so some of the little magnets can point up and some of them can point down, and that's a way that we can encode information. And if all of them point down, then that's one state. If we flip one of them up somewhere, we can encode another large number of states. And really, by putting them in any possible configuration, we can encode all sorts of different information. But the point here is that intuitively, the amount of information that we can store is proportional to volume, because the amount of stuff in here is proportional to volume. Now, if we think about this and take this a little bit further, what we're really doing here is we're saying take space and chop it up into tiny little pieces. We're going to store some fixed amount of information in each little piece of space, and then put that together to get an information capacity that scales as volume. And whatever the constituents are, whether they're little magnets or something more exotic like quarks or whatever, the philosophy is that we're cutting up space and enumerating all the possible configurations the physical state can be in that space, and that's how we're counting how much information there is. So the reason why that's important is that it seems to be wrong at a fundamental level. So the first very explicit hint that there was some sort of revolution coming in our understanding of gravity and quantum mechanics was Bekenstein's observation in 1972 that it seemed natural to associate the total information that can possibly be inserted into a black hole as the area of a surface bounding that black hole in these fundamental Planck units. And this turns out to be a big number because L Planck is a small number, but it's proportional to an area, not to a volume. And it's really a capacity. The reason why it's a capacity is that you can collapse anything into a black hole. So if I start with a hard drive and I collapse it into a black hole, I shouldn't get more information than I had before. And so this gives a bound on how much information there can really be in some region of space. And it's really a big deal that this scales like the area. It's the event horizon area. The event horizon is this surface of no return. If you fall through the event horizon, you can never come out. Because it says that really in a universe with gravity, the information capacity fundamentally does not scale with volume, it scales with area. So I want to emphasize that at a sort of philosophical level, this is a big deal because when I talk about information, I'm not just talking about things like hard drives, I'm talking about physics itself. So what is physics? Physics is about describing what possible states the universe can be in, what possible configurations it can be in. It's just a way of saying like where I can put everything, what are all of the possibilities of what I can have and where I can put it, and how those states change with time. So the reason why physics is predictive, for the most part, is because I can tell you, based on the state that we're in right now, what state a system will be in the future. So this is a bit abstract, but really that's what physics is about. So this is supposed to emphasize it's abstract. Information here is really just a description of a state. So when I say how, say, all of these little magnets in a hard drive are pointing, I'm really describing the state of the physical system that the hard drive is. And so if it's true that really fundamentally the states that the universe can be in are associated with volumes that are areas bounding the region we live in rather than volumes that we live in, then it means that space itself isn't fundamental. Because if space were fundamental, I could say, I've got a cube, I'm chopping it up into little pieces, I'm going to tell you this piece is in this state, this piece is in that state, and I'm going to go through all of the little pieces, tell you what configuration it's in, and that's going to tell you what's going on in that cube. What this says is actually that's the wrong way of ascribing information to space in the universe. That actually you can't talk about volumes filling space, instead all you can talk about are areas. And so in that sense, there's much, much less information in the universe than we might have expected, and the way that we characterize the laws of physics has to be very different. So if you take this idea seriously, as we theoretical physicists have, it suggests that actually at a fundamental level, the fundamental theory of the universe should be revolutionarily different from what you might have expected. Even though it seems like I'm walking around in 3 dimensions, I can go that way, I can go that way, and I can jump up and down. In fact, the fundamental theory actually should have fewer dimensions. The fundamental theory should live on an area instead of in the volume of space. And so this is an illustration, it's a hologram. This idea is called holography, not because it involves actual holograms like what you can make with lasers, but metaphorically because it's the idea that you can have a flat surface that encodes all of the information in a volume, in a region. And if this is true, it means that quantum gravity really is very different, so we don't have to be as jealous as we typically are of people like Dirac and Schrödinger and Heisenberg and Bohr, who got to discover something very revolutionary and fundamental. It seems that if you try to combine quantum mechanics with gravity, you get something more revolutionarily different than, say, just explaining the electromagnetic force. You get something very, 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 very different, and very, very counterintuitive. And so this might just sound like a really crazy idea, and it certainly would be if we didn't have precise mathematical theories where we can compare gravity to some other description of gravity and see that they're the same. And there's this totally unintelligible acronym at the heart of this, which is called ADS-CFT. So the explicit realization of this idea that we have and that in the last 20 years physicists have spent a lot of time playing with connects gravity in a space that happens to be called ADS with something called a conformal field theory. And those are probably both unfamiliar, but I can give you some very, very basic intuition. What a conformal field theory is field theory just means it's like a modern quantum mechanical theory. The standard model is a field theory. Conformal means, the most important part of conformal is that something's scale invariant. That's why here I have a picture of this fractal in object, because a conformal field theory has a symmetry that says that it has to be self-similar when you zoom in or zoom out to longer and shorter distances. That's what the conformal part means. And it turns out that these conformal field theories are theories of gravity. They have a reinterpretation, which is not at all obvious, as particles moving around in a space with more dimensions under the gravitational force, and you can really compare and check both sides of this thing. So I've also included this picture. This is a famous Escher picture called the Picture Gallery, and Escher actually didn't finish it. What's going on in this picture is that it's a self-similar picture, so if you sort of zoom in here, it has a smaller version of itself. But there's a conformal transformation involved in this. So it's not just pure scale, but it's a more complicated kind of transformation that these conformal field theories are symmetric with respect to. And so it's just a cool illustration. So Escher wasn't able to finish it because he wasn't able to figure out exactly how to connect the dots to make this work. But some mathematicians took the picture, computed what the conformal transformation that he needed was, and then with computers, finished the picture for him and sort of filled in this gap. So this was actually an unfinished picture with a gap here. The basic idea is that these scale invariant field theories are actually, shockingly, theories of gravity. And the most basic question you can ask and should ask is, how is it possible that a three-dimensional space is the same as a two-dimensional space? Or how is it possible that a theory living in 2 dimensions actually has a third dimension? And roughly speaking, you can think of this as the extra dimension being zooming in and out of this scale invariant theory. So not only can you move around in the sort of x direction and the y direction, but you can also zoom in or out of the picture. And that's roughly the sort of origin of this extra dimension in the gravitational theory. So I'm unfortunately not going to, or fortunately, depending on your attention span, going to tell you anything more about ADS-CFT or holography. Just going to conclude by reminding you that reductionism has been extremely successful for discovering the standard model of particle physics and the 3 forces other than gravity that we know so well. But black hole physics seems to mean that gravity has to be very fundamentally different, that reductionism just doesn't really make sense. Even though there's this new, very short distance associated with gravity, it doesn't make that much sense to try to take it apart, like we were able to take apart other particles. And that theorists like myself are currently trying to use this holographic principle to understand quantum gravity more completely, and in particular to understand things like black holes, how they actually encode the information that they contain, what happens when they Hawking evaporate, which is a whole nother subject that I haven't touched on, whether they really preserve information or destroy it. We believe they do not destroy information, but that's another talk, so I thank you for your attention.
We do have time for some questions, and there is a procedure which many of you may be familiar with. We have some runners with microphones, and they will bring the microphone to you if you raise your hand. And when you get the microphone, you please stand, tell us your name, and tell us if you're a member, and ask a question. Save speeches for later. And it's important to use the microphone because this is being recorded, and we do want the people who are watching in the live stream and later listen to the video to be able to hear your questions. We'll start with Carl on the red microphone.
Carl Merrill,
Speak up.
I have a fundamental question, and that is that about 2 weeks ago in Nature Communications, there was an article about one of the effects if one could achieve quantum gravity. And it argued that then it would have to obey quantum rules, including Bell's inequalities, and then causality would be a victim of that. And I wondered if you could comment on that.
That's a really interesting question. I would say that we're very confused about this question, but it's something we're all trying to understand. So one of the properties of physics that's pointed to by this picture of a volume is not just that there's stuff in these filling the volume of space, but also that stuff interacts with stuff that's nearby it. So magnets mostly interact with magnets that are close together, and long-range forces fall off. And this is a very fundamental property that we think of as locality, that physics is local, stuff here and stuff there decouples when we separate them a lot. Now, this picture of holography, where one of the dimensions in which we can separate things isn't fundamental, somehow it's emergent, it comes out about from this conformal field theory, it calls into the question, well, is physics exactly local, or is that only an approximation? And I think the real answer is we don't know exactly. We believe that it isn't exactly local. We think that the non-local effects, though, are probably very, very, very small. People call them non-perturbatively small, which is a word for really, 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 really small. But we do think that they probably are there. Some work that I did in the last couple of years was aimed at trying to actually see this by looking at an experimental observable that you could measure if you had sort of godlike powers, and looking at, does locality get violated in this observable? And the answer was there were these tiny effects that could violate it. I'm not sure whether it violates causality. It's a little bit of a hairy thing to separate those two things. I mean, if you could influence something very far away instantaneously, it seems like that could violate causality due to relativity. But it's less clear. One thing that is totally clear is that the conformal field theory itself is causal. So its description is causal, which means sort of if you wait long enough and do experiments over a long period of time, physics should be causal. But in a quantum gravitating universe, we don't know, and it's a very interesting and important question.
Black microphone, please. Stand, tell us your name if you're a member, and ask a question. It's on, just hold it close to your mouth.
Hello, my name's David Lewis. I have a question for you. What's sort of the theoretical role of the second law of thermodynamics on the dynamics of these holographic topologies?
So the second law of thermodynamics is a property of sort of all large physical systems, all systems with a lot of different moving parts. So the second law of thermodynamics applies to these holographic theories because they're ultimately just ordinary physical theories. But it doesn't have any special role. The one thing that's special that I'll mention, since you asked about thermodynamics, is that black holes are supposed to have a temperature. This thing that I've been calling information is the black hole entropy. Those are thermodynamic ideas. A black hole with some temperature in this holographic description just corresponds to ordinarily heating up the holographic theory that it's being described by, the conformal field theory. So there is a nice description of how black hole thermodynamics and black hole temperatures map to those same features in a holographic description.
Blue microphone.
Bob Terry, a member. My question is fundamentally, how do you refute this picture? Are there tests you can make that could refute it? Have any of them been survived? What are the experiments that really point to the need to go in this direction?
So if your goal is to build technology or do things on Earth, I would say that, and you're really thinking about quantum gravity in our universe, there's absolutely no need for any of this. There aren't any gravitational experiments or effects that we're going to observe that are essential for this as we understand it now. It's possible that actually there's something really, really great that we can observe that I haven't thought of, that people haven't thought of, but that's really the straight answer. The answer that's pretty straight, but also roundabout, is that this holographic duality, people call it a duality because it says that one thing and another thing that you thought were totally different are actually the same. This holographic duality connects gravity on the one hand with this other thing, conformal field theory, that might seem esoteric. And actually conformal field theories are extraordinarily common in physics. So literally magnets, I kept mentioning magnets, but literally magnets, if you tune them to their critical temperature, are conformal field theories. Water at its critical point. So there's some point where liquid water and gaseous water are the same. If you go to really high pressure, really high temperature, you can do that with just water. Water behaves like a conformal field theory at that point. So the fluctuations of water, all of the dynamics of water are conformal field theory. Now, that means that conformal field theories are at least sort of common in condensed matter physics. You can make them in condensed matter physics. There are experiments in condensed matter physics that study conformal field theories. And a thing that I think is not, I mean, I shouldn't at all oversell it, but a thing that is not completely vacuous is that some of these conformal field theories that you might care about or be interested in say, condensed matter physics, can be approximately described by gravity. So that's going the other direction. Instead of trying to understand gravity with conformal field theory, you can try to understand conformal field theories, which you actually can make in a lab, using gravity. And this is some approximate description. We don't know, it's not necessarily that great, but some people, even condensed matter theorists, have thought that this provided useful insights in how to understand things like high temperature superconductivity. And that's an ongoing area of research people actually study. So in a certain sense, you could imagine testing this holography idea by going in the other direction and using gravity to understand other systems that we really can make. But in terms of the goal of understanding gravity in our universe, I don't think that there are any ways on the horizon that we can test this.
I have two questions online, and if you're in the room and you have a question, put your hand up long enough for the microphone to come to you. Online questions?
We had 60 viewers tonight via YouTube. The first question is from Jack Martinelli, and his question is, how would you contrast gravitational redshift against electrostatic redshift? And he's not a member.
I apologize. I'm not sure that I understand the question. If maybe one interpretation of the question, if he means if I have light waves, then light waves redshift. Like I can, if I move in the direction of a light wave, then it appears redder to me. It looks so. In the same sense, there are gravity waves, and gravity waves also redshift and blue shift. So in that sense, they're the same. They're both basically just fluctuations, little waves that move at the speed of light, and they both redshift and blue shift are kind of the same way.
The second question is from Joel Wilson. He is a member. His question is, you mentioned using the ADS CFT correspondence to get at the problem of a quantum theory of gravity. Does his approach allow for gravity to be mediated by a spin-2 boson? I'm asking this because a quantum theory of gravitation should be unified with the standard model.
I mean, absolutely. So that's a rather technical question. So one way of, if you were an expert, that you could have said, oh, well, this whole preamble of this talk is kind of silly. Gravity is obviously not similar to electromagnetism. Is that the photon has angular momentum. It has a fundamental angular momentum. It has angular momentum 1 in units of Planck's constant. Some other particles you're familiar with also have angular momentum. So electrons have a half a unit of angular momentum. It turns out that the graviton, the particle of gravity, the fluctuation of a gravity wave described quantum mechanically is a graviton, has 2 units of angular momentum in these fundamental Planck units. I guess that's the background. That means that gravitons are very different from photons and weak bosons, et cetera, in that respect. The ADS-CFT correspondence does describe quantum gravitons as spin-2 particles. So on the gravity side, they're just spin-2 particles. I can give you a very technical answer for what they are on the other side. They're the stress energy tensor of the conformal field theory, which also has spin-2 or angular momentum 2. So that is an important feature, and it's certainly preserved in ADS-CFT. I should also say I didn't in any way discover ADS-CFT. ADS-CFT was discovered in a series of papers in sort of the late 90s, 1997, most famously by Juan Moldacena, who I believe has addressed this.
He has. Okay, do we have the red microphone anywhere? Somebody with red microphone?
Yes. Hi, this is Peter Kessler. I'm a member. This might be amateurish to ask, but several years ago I was reading about brain theory, and I was curious if there's a connection to the idea of this duality of the holographic approach, and do you think an artificially intelligent Escher might help out?
So absolutely is the answer to that question. So
Don't turn it off.
Actually, the way that ADS-CFT was originally discovered, the very first paper by Juan Moldacena, was Juan was studying a particular phenomenon in string theory. So there's a long history here. There was string theory. People realized that string theory actually contained these extended objects called membranes, or D-branes, which are sort of these just membranes that can kind of fluctuate in space. And Juan asked a very simple question, which is like, okay, so we have these membranes. What happens if I just put a bunch of them on top of each other, like a deck of cards? And he and many other people were sort of playing around with these ideas. But he sort of reached the kind of right way of thinking about this first, which is, oh, wow. There's 2 ways of thinking about this stack of membranes. One is via conformal field theory, and one is by thinking about these membranes interacting gravitationally. And he realized that those were actually 2 different pictures of the same physical phenomena. They were 2 different descriptions of the same phenomena. And that was really how ADS-CFT was discovered. Very, very quickly after that, other people, there were other people thinking about similar thoughts, realized that this was actually more general. So what Juan was talking about was one very specific realization of specific kinds of membranes and a specific kind of string theory, but actually it was a much more general phenomenon. That's something we've sort of been unpacking in the last 20 years. When this was first discovered, it was very connected to these membranes. And it was very much like, well, if I have this kind of membrane, I get this thing, and if I have this kind of membrane. And I think it's slowly emerged that it's really a very general phenomenon that just involves symmetry and gravity, and it's quite universal.
The black microphone and then the blue. Who's got the black microphone? There you go.
Hello.
Then blue, then red.
Hello, my name is Adam. I am not a member. Strangely enough, the first question I had has already been asked. So, but another question I had, I remember a while back in my physics education, I read that passing like a quantum mechanical, like something on the quantum mechanical scale through a gravitational potential can actually like change its phase. And that was the first time that I kind of believed that like, oh, gravity does interact quantum mechanically somehow. Does that have any connection with this at all? Could that have any possible connection?
So that's, I think you're referring to like a really great set of experiments that are really, really important in all sorts of ways. I mean, the kinds that I'm thinking of are like, there are these atomic fountain type experiments where you can, so something that everyone probably has maybe heard of is interference of light. So there are interferometers where you send two light beams in different paths and then you interfere them and you can measure properties based on the sort of subtleties of how these light waves interfere. We can now do the same thing with atoms. So you can take a bunch of atoms and cool them down so that they're in all the same quantum state, and you can send their quantum mechanical wave function one way and another way and bring them back together and watch them interfere. And if there's very, very minute forces on one branch of the wave function but not on the other, such as different gravitational forces, then you'll get an interference pattern of these atoms. And this is a way of making incredibly, incredibly sensitive detectors. So there are planned experiments looking for gravity waves using this atom interferometry idea. To sort of be negative, though, there's a sense in which, well, I don't know. I mean, there's a sense in which this isn't really telling you anything about quantum gravity. This is telling you about the quantum mechanical wave function of these atoms given a fixed sort of external gravitational force. And you could view that external gravitational force as just a classical phenomenon. It doesn't matter whether the gravitational force itself was quantum mechanical or classical. So in that sense, this actually doesn't tell you anything about quantum gravity. It tells you about the quantum mechanical system with a classical force on it.
Blue microphone is next.
Hello, my name is Bill. I am not a member. The question I had is about the relationship between the anti-de Sitter space conformal field theory, the ADS-CFT, and the real world. So anti-de Sitter space is not the geometry of the real world. And so what exactly, how do you go back and forth between them? Is it exact, or is it just a model, an approach to be used at the moment?
Yeah, that's a fantastic question. So in some broad sense, there are kind of three ways that the universe might be curved. You can have a perfectly flat universe, which is actually the idealization that we very, very often use in particle physics. And you can have a de Sitter universe, which is the kind of universe we live in, which is exponentially expanding and has a positive curvature. And you can have an anti-de Sitter space, which has a global negative curvature. So it's sort of like a hyperbola. We live, it seems, in, well, a very much evolving cosmological space-time that's more like de Sitter space. During inflation, we were in something very close to de Sitter space, and now it seems like in the future, we know that we will be in a universe that's exponentially expanding. So that's different. The anti-de Sitter space is it's sort of like eternal and fixed, and it's a different space-time. So if you want to, it depends on what kind of question you would like to ask. So if you're interested in questions about cosmology, then ADS-CFT does not answer them. And trying to think about quantum cosmology, the interaction of quantum gravity with cosmology, what the real origin of the universe was, etc., is really an open problem that we don't have anything as useful as ADS-CFT to address. But if you want to study gravitational phenomena in some finite region, like say I want to make a black hole and watch it decay in our universe or elsewhere, then I think it seems extremely reasonable that you can use ADS-CFT for this. The reason is that in ADS-CFT, there's a negative curvature in space. So space-time is sort of saddle-shaped. But any curved surface, if you zoom in to very short distances, looks approximately flat. So if you're doing experiments that are small on the scale of the universe, it sort of doesn't matter very much whether the universe is positively or negatively curved or not curved at all. And with something like the ADS-CFT correspondence, you can take a limit where really this curvature gets as small as you'd like it to get. And in our universe, you can't take that limit, but the scale of our universe, the curvature is sort of the Hubble scale, which is truly enormous. It's much bigger than superclusters of galaxies. So if you're trying to sort of do an experiment in a lab, if you had the technology to make a black hole and watch it decay in some small region, it seems like the sort of macroscopic structure of the universe far away wouldn't matter that much for that kind of experiment. There's sort of a decoupling between things that are incredibly big and things that are in some finite region. So that's why we think that conclusions about, say, what happens with a black hole based on ADS-CFT probably also apply to black holes in our universe, et cetera. But it's absolutely true that ADS-CFT doesn't tell us sort of what the rules of the game are for, say, the origin of the universe with the Big Bang and things like that.
So we're going to go 3 more, red, black, blue.
My name is Shivaji Seth. I'm not a member of the society. So I was also thinking about the space-time curvature. And you mentioned this emergent extra dimension. And I'm trying to think how the curvature, I mean, quite simply, could at the fundamental level, the curvature could emerge from this dimension. And doesn't this mean that there needs to be some interaction between the fundamental particles, matter particles, and space-time, perhaps?
So, I mean, I think the answer to your last question is yes. So, I mean, general relativity is kind of describing the interaction of space-time with matter. So, matter tells space-time how to curve, and then the curvature of space-time tells matter how to move. That's a sort of famous description of what general relativity does. And when you combine general relativity with quantum mechanics, that doesn't go away. I mean, classical gravity should be and is a limit of quantum gravity. And it's just that the space-time itself has its own quantum fluctuations. At a technical level in this holographic correspondence, I'm not sure exactly sort of what the useful answer is. One comment is that in ADS-CFT, I said that the important idea is this scale invariance of the conformal theory. It's that if you zoom into the conformal field theory, it's symmetric. And that fact about the conformal field theory is actually encoded geometrically in anti-de Sitter space. So the reason why it's ADS in conformal field theory is that space-time symmetries associated with the curvature in ADS are associated with this conformal symmetry of the conformal field theory. So in that sense, the sort of curvature of ADS is built into the conformal field theory and vice versa.
Last question. Blue microphone.
And my name is Peter Bishop. I'm not a member, but I'm a computer guy. So I'm interested in information. And so you were showing a disk drive there. I sort of think of DNA as being a digital storage mechanism also. But both of these things don't quite follow what you were saying about taking space and chopping it up into pieces, because once we get to below the size of about an atom or thereabouts, all of a sudden we can't store our information in it anymore. And so if you take a strand of DNA and you turn it into a black hole, now it's lost all of its information. And so I don't quite understand how you're saying that when it goes into a black hole, you don't lose any information.
So I mean, well, there are a couple parts of this question, but I think the important part is that there's a conceptual leap from hard drives to thinking about the laws of physics in terms of information itself. So I guess maybe the best answer is that, one answer is that if we were much, much, much more advanced, then we could store information in a much more powerful way by having some quantum system and putting it in a particular quantum state, and that defining how we were storing information. So when we talk about DNA or a hard drive, we're actually just storing information. Classically, we're not enumerating all the possible states the system can be in, because if you try to do that, you'll break your information storage device. It's not useful to store information if you can't reliably do it, and you can't reliably do it unless it's really robust. And for it to be very robust, you either have to insulate it from its environment, or you have to find some reason why it can't change, so that when you put the information there, you can get it back out again. But if we were very, very much more advanced, then maybe we could use all of the innumerable quantum states that a system can be in to store information. And then we'd be able to store much more information than we currently can now. And so there is a conceptual leap from how we practically store information, which is actually always classically, I believe, to this conceptual idea of what the possible states are in nature.
I think you're going to have to come back and give a little more explanation of some things. But for now, thank you. And before you go, I'd like to present you with a couple of tokens of thanks for coming here and giving this lecture and getting us all thinking about quantum gravity.
Thank you very much.
We have a framed copy of the announcement of your talk signed by the members of the General Committee on behalf of the members. And we also have a signed copy of the Volume 1 of the Bulletin of the Philosophical Society of Washington, we now fondly know as PSW. It has the reasons that the organization was founded and why they chose the name Philosophical Society and the original members. And as Nima pointed out, an article on how to calculate pi to 31 places. So thank you very much.
Great. Thank you very much.
Before we go and adjourn to the social hour, we have a few closing items. PSW depends on members and sponsors. If you're a member, please note that the 2019-2020 dues notice has been sent. And if you have not yet paid your dues, please do. And please consider making an additional donation, sponsoring a lecture or series, and volunteering to help carry out the Society's activities. If you're not a member, please consider joining. You can apply for membership on the PSW website. It's pretty easy. Just go to the Join button on the home page, which will bring up this page, and there is Apply for Membership, and the application for membership will come up, which you can fill out, and you fill in all the forms where there are red asterisks, and submit the form, and then pay your dues. If for some strange reason it turns out that you shouldn't be a member, we will refund your dues payment. In truth, all that's required is a real interest in science. As Peter knows, we sometimes tell people who tell us they're interested in philosophy that we don't really deal with Hegel and Kant and Aristotle and Plato. But other than that, if you're interested in science, you're welcome to join. So please, if you're not a member, join. If you have any questions about membership, please see Membership Director Lloyd Mitchell, our local gene hacker, and corresponding Secretary Robin Taylor, who's hiding back there behind the audio rack. You can also make donations on the website. PSW is a nonprofit educational organization. It's tax exempt under Section 501c3 of the Internal Revenue Code, and contributions are tax deductible to the extent permitted by law and the Internal Revenue Service. All PSW members in good standing may wear the PSW rosette. If you wish to purchase one, it's $15 plus tax, and you may do so at the rosette table from our social media director, Ann McQueen. Upcoming lectures. Our next lecture is going to be on space architecture for a moon village, designing for space habitation, by Daniel Innocente. Daniel is a senior architectural designer at the well-known architectural firm Skidmore, Owings, and Merrill. How many of you have heard of SOM? Okay, well, they're a storied firm. They design many, many famous skyscrapers, and they're the designers of, I think, half of the world's tallest buildings. And we had a wonderful talk here not long, well, a couple of years ago. It's probably 10 years ago, I don't remember. by William Baker, who was the chief engineer on the tallest building in the world, the Burj Khalifa. We don't know yet who is going to be the speaker. And this is a great graphic that Daniel provided to me. And this is based on their design for the Moon Village that I'll be talking about next week. October 4th is a bit up in the air at the moment. After that, we're going to have a talk by Neil Devaraj, a professor of chemistry and biochemistry and bioengineering at UC San Diego. He'll be talking about bottom-up synthetic biology. On November 1st, we have a report on results from tests. The Transiting Exoplanet Survey satellite was launched about a year ago, I think, and has results that are appearing in the news. The lecture will be given by George Ricker, who is the principal investigator for tests and also directs the CCD lab at the MIT Kavli Institute for Astrophysics and Space Research. On November 15th, we're going to have a talk by Dean Romich, who is a distinguished professor of oceanography at the Scripps Institute of Oceanography at the University of California, San Diego, and he'll be talking about the Argo flotilla. If you don't know about that, it's a flotilla of about 3,000 sensors that autonomously float in the Pacific Ocean and periodically submerge themselves to a depth of several hundred feet and then resurface slowly, taking measurements of temperature, salinity, and currents. And when they get to the surface, they deploy an antenna and report the results back. And they are currently providing the most comprehensive records of ocean parameters that's ever been assembled. And it's a model for these sorts of networked autonomous sensor platforms for monitoring the environment. So that should be a very interesting talk. And then we have, on December 6th, rounding out the year, a talk by Harold Hess, who's a group leader at the HHMI Genelia, formerly Genelia Farms, a mapping of brain circuits. And that should be very interesting. It has to do with using super resolution microscopy and fluorescence to map individual neurons in the brain on a large scale at the single cell level. And with that, let's please thank tonight's crew, Connor Nixon, and I want to point out for all of you people who are really sensitive about the use of terms, this term here, best girl, that is a term of art. In the movie making business, there's a particular job on the set called best boy. And now that there are a lot more women than there used to be, the women who do that job are called best girl. It's an important job. In no way belittling Laurel, who is our volunteer best girl tonight. So thank you, Laurel. And with that, I will take a motion to adjourn the meeting to the social hour. Bob gets this motion. Carl seconds. All members in favor? Aye. All members opposed? The meeting is adjourned to the social hour.